Today we're going to look at an example that involves intersection points between a line and a curve. So for example, find the range of values of k for which the line y equals to kx plus 4 does not intersect the curve y equals to x squared minus 4x plus 5. Also state the value of k for which y equals to kx plus 4 will be tangent to the curve. So I have a quadratic curve and a line, and I need to find the values of k. Okay, in the first part, in which the line does not intersect the curve. Okay, let's do it first. Okay, so what is this all about? Let's draw a graph of the line and the curve. So I have the quadratic curve here. Okay, y equals to x squared minus 4x plus 5, and the line. Okay, y equals to kx plus 4. So if you notice k is actually the gradient of this line, right? So when I vary the value of k, I'm actually varying the steepness of the line, as you can see in this line. Okay, when I vary k, when I increase k, it's getting steeper. When I decrease k, the line is getting less steep. Okay, until it turns negative. Right. So in the first part here, find the values of k such that it doesn't intersect the curve. So here, okay, let's say for example, when k equals to 0.9, it cuts the graph. Okay, the other graph at 2 points. But if I increase it further, it still cuts the graph at 2 points, right? However, if I decrease the value of k until a certain point, like here, you notice that the line doesn't intersect the curve anymore. Alright, so I need to find those values of k such that this happens. So it seems for now that k is between like -2, right, maybe to -6 or -5. Okay, let's try to do this algebraically. So in order to do this, first we note that if we want to find the solutions of the points of intersection, we need to solve these two equations simultaneously. Alright, so first of all, I let kx plus 4 to be equals to x squared minus 4x plus 5. Once we simplify this by bringing all terms to one side, I have x squared minus 4x minus kx plus 1 is equals to 0. And rewriting this, I have x squared minus 4 plus k x plus 1 is equals to 0. In order for the curve not to intersect the line, this equation must not have real roots, right? If it does, it means that this curve and the line must intersect one another. So for this quadratic equation to have no real roots, this implies that the discriminant b squared minus 4ac must be less than 0. Okay? Let us try to solve this inequality to find the values of k. So when I expand out 4 plus k squared, I get 16 plus 8k plus k squared minus 4 is less than 0. So k squared plus 8k plus 12 is less than 0. So from what we learned from quadratic inequalities, okay, first we factorize this to get k plus 6, k plus 2 is less than 0. From here we sketch the curve. Okay, so I have two roots, both negative. Okay, so Okay, if I let y to be k plus 6 times k plus 2, this will be the quadratic curve. Now, since this is less than 0, okay, the values of y less than 0 will be the part under the horizontal axis. So hence, k is between -2 and negative, it should be k is between -6 and -2. So this is my solution for the first part. Now for the second part, also state the value of k for which the line will be tangent to the curve. So in order it to be tangent to the curve, we just continue from here. Okay, from this equation here, instead of having no real roots, we must have 2 equal real roots, right? Because we want it to be tangent. So in this case, I let the discriminant d to be equals to 0. So in other words, okay, if I go through the same steps, I'll get k plus 6 times k plus 2 to be equals to 0. So we solve it, k equals to -2 or -6. So that concludes the second part. Now let's verify this from the graph. So when k is negative, alright, let's move on to -6. So when k is -6, you see that it touches, it seems to be tangent to the curve, right? It seems to be tangent. Okay, when I increase it, it doesn't touch anymore. Alright, it doesn't intersect the curve anymore until when I get to k equals to -2. Then it is tangent again. But if I increase it further, it will always intersect at 2 points.